All right, so this is your week 2 of your live session for problem solving in advanced quantum mechanics with applications. So yesterday we had our first live session. So where we just reviewed some of the basic problems of quantum mechanics. So that was uh, basically related to your quantum mechanics course level 1. So today we will move on to some additional new topics which perhaps maybe not you are familiar with somehow at this point, or maybe if you had seen the lectures already, you could have you can guess that there are some few couple of new topics. So I will be talking about one of them. So that is about coherent states. So yeah. Yeah, this is important in the context of quantum optics. If we want to know more about modern optics and its related research, then coherent states are really essential. And yeah, and all the laser technology is all about these coherent states. So yeah, uh, we'll look on to some related problems, and we'll start with some uh, brief overview about the coherent states. So uh, hello, Amarchan, could you able to hear me right? uh, if I'm clearly audible to you. Hello. uh, I just wanted to confirm whether my voice is clear, or having any other noise around, or is it clear? Amarchand, if you can uh, let me know. Uh, I've just checked moments ago. Like uh, it was fine then, but hopefully it is still. So okay, like I guess, yeah. So as I was telling you about that this session we will mostly talk about these coherent states, and we'll see some problems that could help you understanding the idea behind a little bit more clearly. And also you can try looking into some new problems uh, side by side. You can also see the problems which are asked in your assignment, and you can correlate various things from this session. And also like if any problem of anything that you are facing till this point, like you have covered at least 2 weeks, and also week 3 is already starting. So oh, okay, thanks Amarcha. Okay. So yeah, so if any issues, if anything not able to, like you are not able to follow properly at any section or at any part of this uh, course that has been running till this point, so yeah, please let me know, including assignments or anything else. So yeah, so what about coherent state? So as we try to like define what are coherent states. First important property of coherent states are they are made of indefinite number of quanta. So if you remember the number states. So the number states, like if I uh, okay, if you remember about the number states. So uh, the number states which I hope you are already familiar from the quantum harmonic oscillator system, which is represented by n, ket n. So this number states like denotes fixed number of state. So this denotes fixed number of state. So, but coherent states, like coherent states, and you will see that we will be denoting it with something alpha. So they are made of indefinite number of states, uh, indefinite number of number states, you can say. So, so it has indefinite quanta. So yeah, and but number states has only finite number of quanta, some fixed quanta, and as so, and these are basically, you will find that coherent states will basically form a linear combination of this indefinite number of n states. This is the linear combination. So yeah, so it's just basically alpha, some C1 0 plus C2 1, or I can write it C0 C1. So yeah, it will keep going, like there are indefinite number of. So yeah, if there's any problem, you can speak. Feel free to speak. Uh, uh, and um, and you will find that, like if you remember, the end states, they were these states. So these states were eigenstates of, uh, or let me uh, okay, so if you remember, so these states, these were eigenstates of Hamiltonian. So H, uh, these were energy eigenstates. But and here you will find that, uh, uh, hello, yeah. So there's nothing problem with my voice, right? Uh, so all of you can hear me right properly. Oh. So Amarchan, like you were trying to letting me know. Yeah. Okay. Thanks, Arup. Yeah. Okay. Yeah. So as I was speaking, that these number states are basically the eigenstates of Hamiltonian, which we are already familiar from quantum harmonic oscillator system. And here, if you see for quantum harmonic oscillator system, these coherent states, these alpha, are basically eigenstates of one of the ladder operator, of lowering ladder operator. So okay, and um, so yeah, so if you see, this is the eigenvalue equation for the coherent state, corresponding to the lowering ladder operator. And if you see this alpha, which we are trying to say here, so this alpha is some complex number. So this is some complex number. And one of the very crucial point about this coherent states, unlike this number states, so which denotes like fixed number of quanta. So coherent states itself, as it is made of indefinite number of number states, their linear combination, it itself gives rise to a classical nature. I mean, you will see a classical nature will manifest from these coherent states. So, so like for example, as I was also initially mentioning, these coherent states are important when you try to understand the physics about quantum optics or the modern optics, or in particular about laser physics. So there we mostly we talk about these coherent states. So these coherent states, like even as we know, like when we talk about lasers, like we talk about photons and there are various mechanisms like this metastable states and the other things that which we read in detail about the laser physics. So you will find like we are talking about a quantum picture because we are speaking about photons and everything. And uh, and but uh, but even how you will see that like that I mean the light that we describe in in lasers is again it's something that attains a classical nature, and it is because of these coherent states that we use in the laser physics to describe them. So this alpha is
Sir, I have a doubt.
yeah, sure.
Sir, you said that that it is a iron vector for the lowering ladder operator.
Yeah, it's an
But
eigenstate of
yeah, but the ladder operator can change the eigenstate, right? Let's say if it is n, it can change into n minus one or n plus one like that. So how can it would be a eigenvector?
yeah. I'm not telling that this ladder operator A is a. I mean, I'm not telling that the n is a eigenstate of ladder operator A, because as you are telling, so just now you just said like if I operate A on n, so it will go to n minus one. So okay, so this will be precisely something uh, square root n minus one. So this is definitely not a eigenvalue or a, yeah, this is not definitely an eigenvalue equation. So and this is not and you cannot say n this ket n or this state n would be a eigenstate of this lowering ladder operator. But if you operate A on alpha, then alpha can be your eigenstate because when you operate A on it, you get A alpha, A state alpha back again. Sorry, alpha alpha. So where alpha is something given like this, so which is some number, which basically the magnitude explains. The magnitude basically gives you the uh, um, so this is a complex number. In general, this is a complex number. Its magnitude basically gives the excitation of the photons, the average excitation value of the photons, because it is made of indefinite number of photons, indefinite number of n states, and the phase, there will be a phase because it's a complex number. So the phase basically describes the yeah. So this is just the phase. So you will find that like I mean the the excitation of photons or the photons, this alpha which is made of, it's like it will have a oscillatory nature. So something like which we know like even when we try to explain electromagnetic waves or the light, there also we use this oscillatory type of plane wave type of expression, like some oscillatory equation. So there also we have a amplitude and a phase. So same in the same way we also have something similar here for alpha. So we will see in more precise way in one of the problems. So yeah, I'm talking about alpha is a eigenstate of A, not n is a eigenstate of A. So is it like I'm able to clear your point or
It's like it's a linear combination of those states, so it can be eigenstate of A. That's what
uh,
you mean.
uh, yeah, it can be eigenstate of alpha, but it is not necessarily an eigenstate of a number state n.
Okay, sir.
Yeah, okay. So yeah, uh, yeah. So we'll see like how I mean why it is called so as coherent. uh, like coherent as we I think that name, like I'm probably may not sure or may not remember it properly, but since the classical nature, like when we talk about classical nature, I mean like the classical nature has to no, I mean, like when we are trying to explain quantum systems, so if we use these states, then the behavior of that quantum system, you will find that it will manifest some sort of classical nature, and from that classical idea, like it is like we are calling it as coherent. So like I'm not sure about that name, but this is something I feel like, if I remember properly, or maybe not, like uh, yeah, okay, yeah. uh, so it is like I mean, like for example, if you remember, like we were talking about some expectation values in our last class. So while we were uh, like doing this, when we were computing these expectation values, like we were taking some this we were taking this position operator, and we are sandwiching it with some state. Let's say n is your number state. So this will give you something like if you remember, like it was used to express something as a plus a dagger. So I mean, uh, so we have done a similar problem like yesterday. So like if you find this, like it would give you something, I mean, like yeah, it would give you some result, but which we have seen even last time. But if you do this instead in like for example, in coherent state, if you do this where alpha is your coherent state, then you will find let me just create some space here. Okay, so as I was talking about, like if you take this position operate, if you take the expectation of position operator in coherent states, you will get something. The result you will find out to be something x naught sine omega t plus phi something. So so this is like a like the behavior of light itself. So the behavior of classical light. So it's not like the result is not in terms of quantum numbers or something. Like this is not the outcome is like something of oscillatory type behavior. So it is clearly giving you some classical nature coming out of these coherent states. So we'll see like in a little bit in more precise way in one of the problem ahead. So yeah, and like for example, um, if you see like what one of the like trivial example where you will find where you can guess one of the very straightforward way to guess about coherent state is this zero state, this zero number state. It's a, you will find that this is a coherent state, because if you operate uh, a on 0 equals to 0 0. So uh, so this is like, as I said, like a when operates on alpha, it gives alpha alpha. So where from this definition you can say that 0 is a coherent state. And also as I said, like it's a very special, or rather a very trivial case. So as I also said, like coherent states are something that is given in terms of linear combination, like c0 0 plus c1 1 plus c2 2 and so on, because it contains indefinite number of quanta. So this zero can also, you can trivially you can something write it as 0 0 1 0 2. So it's, since it is a very special case, so it is uh, all the this transition coefficients will basically be having 0, and only one of the transition coefficient, or basically this 0 itself collapse to a only one particular ground state, and it is still a coherent state because it obeys this eigenstate relation. So it's a one of the trivial example of coherent state. So yeah, but we'll see how we can construct coherent state like up next. So this is some few of the important points of coherent states. So which yeah, and how it is different from number states, so which I just try to point out. And yeah, and there are I think maybe there are even you will find more interesting points or comments about this coherent states. You would have seen a detailed explanation in your lecture videos, you can check them. So yeah, is there any question? Hello, you can speak if you. Okay, then how to construct these coherent states? So we can um, basically construct these coherent states. Uh, yeah, we can uh, uh, to construct alpha. We need this displacement operators. So this displacement operators, what they do, like as the name suggests, like it helps us to take, like suppose if we have a uh, uh, right, suppose if we start from uh, let's say uh, like how can we let me just give me a moment, like I want to check this is correct or not, like this is okay, okay, this is yeah. So yeah, as I was telling you that we need this displacement operators. So these displacement operators required to construct coherent states. So like what they do basically, so if we have some let's say we want to create a coherent state from this ground state, like from this zero, like if we want to go to some state that is known as coherent state, so alpha, so we need to use d alpha. So this is the operator we have to do the operation in order to get this alpha, this general coherent states, this alpha states. So we need to if we want to construct this alpha, we need this d alpha, and we'll see more property like why this is exactly called displacement. Like maybe in the next some questions we'll have. And and one thing we'll note here that and also as I have written down here, that this displacement operator, which is defined to be this exponential of this alpha ladder operator, this raising operator alpha a dagger minus alpha star a. So this, you remember, this is something exponential of some operator. This is not something exponential of some number, some complex some complex number or integer or something. So this is a very different object. This is mathematically a different object, like this is exponential of some operator. So this means this is itself is some operator. And this operator can also be written down in this way, where you have the first factor is exponential of minus half of alpha square, which this is a number something, because alpha is some complex number, so this is some complex number, uh, or basically we are taking magnitude of alpha, so this could be some real number. And then you have two other exponential factors, so which both of them are uh, individually some operators. So why I'm telling you this, that this is something important to note here, because um, like if you have something, let's say if exponential of a and exponential of b, so you have a practice of like uh, using this exponential properties, where you can write this exponential of a and b as a plus b. If you cannot do this, if a and b are operators, you can only do this, uh, let's say if a and b are operators, but commutator of a and b is 0, then you can write e of a and e of b, exponential of b, equal to exponential of a plus b. Otherwise you cannot, like if a you cannot write this if a b does not commute. So keeping this in mind, so there is something a different mathematical identity or rule to it, using how we can deal with this kind of exponential operations. So that is something known as DCH rule. Like let me write it. DCH rule. So in BCS rule, like what we do, so BCS rule is given to be, so this is a mathematical identity. So if you have exponential of a times xb times exponential of minus a, then you can write it as b plus commutator of ab plus half factorial of commutator of A and AB. So this is a nested commutator, meaning commutator inside the commutator, and you will have some higher nested commutator as well. So the this rule will keep on going. But using this rule, like we can deduce some key properties of exponential, which will be useful to us. So if you have exponential of A and exponential of B, you can write it as exponential of b exponential of a uh, times exponential of commutator of ab if uh, ab, let's say let me just make you one more thing clear here. So let's say if uh, commutator of ab is something, let's say c, some number. So basically, or this is C identity operator. Number means it's basically something multiplied with the identity operator, because these are operators. So if it's commutator is some number, then like for example, commutator of x and p, px. So which it's uh, I h bar. So it's basically a number. Uh, so so uh, if a and b, the commutator is some number, then what you can do, uh, 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 you will find that this will go to 0, because commutator of any identity operator is basically 0. So if a commutator of a b will give me some number times identity operator, and then commutator of a and identity operator is basically 0. So similarly, there will be a more higher number of commutators, higher nested commutators. They will also go to 0. So you will have only these two terms survive. So from these from basically you can do a little bit of more algebra here. So from this you can get this. So this next relation. So right. And if you do some more bit of algebra, so the first thing how you can get here is like there's some mathematical tricks you have to use it, so which I'm not going into details, which is essentially not required here much. So maybe I can just tell you some hints, like you can multiply like both sides of the equation by exponential a. So here also you will multiply it with exponential of a, and then yeah, and then you will get yeah, then you have to something do exponentiation, and after exponentiation you can easily get this one. So yeah, and same way you will end up another relation from here, so which like if you take uh, log of this over here and log of this over here, you can get something uh, yeah. So on the right hand side, probably you will get something uh, b plus a plus commutator of a plus b, sorry, a commutator of ab, and then uh, right, and then if you exponentiate again from on the both left and right hand side, you will get another relation which I'm directly writing it. Then probably there would be one more step which I'm not exactly showing here, but you will end up with something exponential of a plus b is exponential of a b exponential of minus a b commutator over 2. So right, so now you can see like when you have operators, you have and also this is, remember, only if commutator of a and b uh, is some number, any number like complex or whatever. So if it is not any number, then this will keep on go. There will be many exponential more terms, more exponential terms. So but you will have only up to this if a commutator of a b is some number. So here we are doing it because we have a like we have a key relation here. So when a and a together, if you take the commutator, it basically gives you something identity, I guess. So that is why we are keeping only up to this. So but the point here is it is not like, as we have simply numbers, when we have simply numbers like if exponential of a plus b, if a and b are just numbers, then we can just directly break it down as exponential of a and exponential of b. So you can only do this if a and b are numbers, or a and b are, if they are operators, then they should completely commute. If completely commute, I mean they should commute right from the first commutation. Like it's not like the higher nested commutator will commute. If the higher nested commutator will commute, then you will only get one more additional factor. So yeah, so that was the point here. So using that, like we can, so yeah, so the displacement operator, which was initially defined to be this. So so the displacement operator, which was initially defined to be this, we can write it as uh, d of alpha. uh, let's say this is something uh, a plus b. Then using the identity, we can write uh, exponential of a. So a means I am talking about this as a. So this is, let's write it as alpha a dagger. Then you have uh, so like there is some noise. Okay, let me. Is it better now? Uh, like it's better. Okay, so yeah, like sorry for that. So yeah, just please let me know if again if there is issue, if the issue is still remaining, like I will try to sort it. Yeah. So when you have so using the this BCH property, or the rule that which we found here, we can write the displacement, or we can rewrite the displacement operator again using this rule right here. So so where like I'm calling alpha a dagger to be a, then the first factor, exponential factor, will be this. Then the second exponential factor would be exponential of minus alpha star uh, a. Then the next is like exponential of minus commutator of ab. So ab is like alpha a dagger, then minus alpha uh, star a, then right, then this is whole divided by 2. And if you compute this commutation, so you will find out this will give you, this commutation will basically give you I think this will give you alpha star alpha uh, minus alpha star alpha identity. So, or otherwise this is basically uh, minus alpha magnitude square. So uh, I think this is what uh, right. So yeah, this is what you will get. So you will have this uh, d of alpha as exponential of minus alpha star alpha squared by 2, exponential of alpha uh, a, then alpha so this is alpha star a, and alpha let me alpha star a, and alpha a dagger, right. So we'll use this like in one of our problems, and this will be more useful than the definition right here. So yeah, so that is like some like brief idea so far about like what are coherent states and how we can build them using this displacement operator. And when dealing with displacement operators, we have to be careful with this exponential business, because this exponential techniques are not as straightforward as we are so far familiar with usual numbers. So now we have to deal with exponential of operators. So that is why we have to deal with this operate with this exponential of operators slightly in a different way. So any questions or anything, any problem not understood, like uh,
Sir, we can always write that exponential term into this equation if the commutator is non-zero, right?
which expression you were talking about, this one?
Yeah, yeah, yeah.
Yeah, you can always write this exponential of a plus b, any operator a and b, or any operator, you can break it down as exponential of a, exponential of b, and exponential of this, only if the commutator of a and b is some number, some number c. If it is not, let's say if the commutator of a and b is some c, so c is again also some operator, like some this is some operator now, then in that case, like it will this expression, this expression will not be only this. So there will be more exponential of terms, there will be more exponential of a and A B kind of terms. So there will be more nested commutator that will appear, which is right now they have all gone to one, I guess here. So that means you only have these three factors on the right when you try to decompose exponential of a plus b. So that is why I was telling, if this c is not a operator, instead this is uh, some number c, some number c, then uh, you can you can call this as exactly equal to this. So that is the essential condition here. Uh, is, clear, or this is what?
Yes, sir.
Okay, yeah. Okay, if there's anything more, you can let me know.
Sir, in this
Yeah,
BCH
yeah,
written
BC.
like exponential, and the B operator is sandwiched between the exponential.
Yeah,
To
B
make
operator
like,
is two exponential, right?
yeah, but there is no exponential terms in the right hand side. Why that is so?
Yeah, yeah, you are right. So there is no exponential on the right hand side, because you can expand it. Like there is this is basically the identity which I have just simply borrowed here. But the identity, like I am not sure how it is proved. So they are basically proved using some they frame out some differential equations and they prove it. So but you can understand maybe roughly, like this exponential of a, you can expand it as something, like you can expand it as something uh, identity operator plus a operator a plus 1 by 2 factorial operator a square, and so on. You can do this, because this is the basically exponential expansion, or basically the Taylor series expansion of exponential. And same, you can expand this here also. So you will have identity minus a, then plus uh, a square, and then minus, yeah, it will go on like this. Then you have these three things. So you will take from the first term, you will see identity operator when operates with b, and then or let's say when b operates with identity operator, it will give you b. And again, identity operator from the left, when operates on b, it will give you b. So the first term is b. So and like this you can get. And in some way, like for the second term, you have commutator of ab. So you can find out from this from this multiplication of these three. You will find out, you will end up with some term which will give out something ab minus ba. So this is basically nothing but this is commutator of ab, which is your second term. So and this way you can get more such terms. So there is no problem if there. Yeah, did you get the point?
Yes, sir.
Yeah, okay. uh, okay, so yeah, so any other questions, like we can still have a little bit more uh, discussion on that if you want, or we can move to some problems. So yeah, if there's any other question, or yeah, you can let me know. Or okay, if there's no more, or if you want to ask later, it's fine. So yeah, then we'll see some uh, more things about displacement operator here. So let's start with the first one. So where we need to prove the displacement operator is basically an identity operator. Sorry, the displacement operator is basically an unitary operator. So when you like for unitary operator, like, or for unitarity of an operator, is when you, let's say if you use your unitary operator, then if you take u of conjugate transpose, that is dagger, with u, you get identity operator. So so these are your operators. So it's the same thing we have to prove for displacement operator. So the displacement operator, let's start with the first definition which we had, displace. So d alpha is your displacement operator. So it is written as alpha uh, a dagger minus alpha star uh, a operator. Then yeah, and if I do the complex conjugate and transpose the I mean the dagger, so then you will have exponential of alpha a dagger minus alpha star a dagger. That means this is exponential of alpha uh, a dagger a dagger. So alpha star a whole dagger. So then that will give you exponential alpha star, because alpha is a number and its dagger means simply conjugate, and a dagger is a, then minus alpha a dagger. So this is the uh, conjugate of displacement operator. And you will see that this is also if d alpha is this. So if d alpha is this, then you can also see uh, this is also equal to d of minus alpha. So what we have here is d of alpha dagger is basically d of minus alpha. So that means what I can write here. So this is also like for a unitary operator, if u dagger u is identity operator, then u dagger is also equals to u inverse. So this is also the property of unitary operator. So here also we have d of alpha uh, dagger is basically d of uh, alpha minus inverse. So if d alpha is a unitary operator, so like um, so that means d alpha inverse should be equal to d of minus alpha. So now you can just straightforward, you can just simply check if d alpha dagger d alpha, if you do this you will get exponential of minus uh, let's say if I take minus common outside, then alpha a dagger alpha a dagger. So d of alpha dagger is this thing. So this is d of alpha a dagger, then minus alpha star a, then exponential of alpha a dagger minus alpha star a. So here you can see this is exactly of something of the form exponential of minus a and exponential of a, and this should be equal to exponential of minus a plus a. Why I can write it? Because a can commute with itself. So if a and a commute, so both are the same operator, so that's why they will obviously commute with itself. So I can write this exponential as this, so there is no problem. So this is like how you deal with exponential of numbers. The same here you can also do, and this is nothing but exponential of 0 is identity operator. So this is identity operator. So now you see that d alpha is a unitary operator. So okay, so any confusion or anything? Uh,
Sir, how can we write d of minus alpha?
yeah. So right. So d of alpha, you can think this is a some function of alpha. Okay. So this d of alpha equal to exponential of alpha a dagger minus alpha star a. So if I if I am now uh, if I want to write d of minus alpha, then what it would be, you have to just think this is some function of alpha, then it would be exponential of minus alpha uh, a dagger, then alpha star. So alpha star means before doing conjugate, you make it minus alpha of conjugate. So this is basically minus alpha star. So minus alpha, sorry, yeah, minus alpha star, this minus alpha star a. So this will basically become equal to exponential of uh, alpha star a minus alpha a dagger, and this is what I think you have when you take the transpose or the conjugate of displacement operator.
Okay, sir. Okay, sir.
Yeah. Okay, so anything not as clear or still you're finding confusing, like, please, uh, you can speak and you can clear yourself. Okay, so okay, if not, then like we can see the next thing what we have to prove right here is when you sandwich this operator a between this unitary operators. These unitary operators are basically your displacement operators. So what you are getting is a operator with alpha. So a plus alpha. So it's basically you are getting a plus alpha identity operator. So what you are trying to do is like your operator a is getting displaced by some alpha times identity operator. So this is exactly like you get like when you are having translation operator, like for example, if you remember, even in your classical dynamics course or somewhere, you would have surely seen this kind of thing, where if you have some operator like uh, ea px uh, multiplied with x and minus uh, a px, so you get something x plus a. So the same way the same way you are also having something the role of this operators used to be displacing this x to x plus a. So you were using these operators to displace from x going to x plus a. The same way the displacement operator is trying to displace this operator to some alpha identity operator. This is one of the property of this displacement operator, and you now can clearly understand like why this we are trying to call it as displacement operator. So these are some special type of unitary operators which in this context are clearly they take the property of displacement, or like they try to displace the uh, ladder operators. So we can call them displacement operators. So um, so we'll try to prove this, like how this is actually can be seen. So let's say again, um, Okay, so again, let's start. What we had is displacement operator. It's dagger a d alpha. So we can write exponential of alpha star uh, a minus alpha a dagger a exponential of alpha a dagger minus alpha star a. Then yeah, so now remember, like we had the BCS rule, like using BCS rule. Uh, so if you remember this BCS rule, which we so this one so using this BCS rule, like we can write B plus commutator of AB and so on. So the same thing we can do here, because it is already similar type of operation we are finding here, where the operator A is sandwiched between these two operators, these two exponential operators. So with that BCS rule, like we'll have A. So this is, let's say, we call this as exponential of A, and this is B, and this is exponential of minus A, or maybe the other way. Let me check. Yeah, it's fine. So first you get B, and then you have commutator of A and B. The commutator of A and B, which means you will have uh, commutator of alpha star A minus alpha A dagger. So this is A with commutator of B. Then you will have some higher commutator. So let me write. So just follow the rule which I have written it before. So the BCS rule. So 1 by 2 factorial. Then you have A alpha A dagger. Then the same thing back again. Let me just copy this. Okay. Then you will have more number of terms. So let me remind you, I'm writing this the entire expression, like following this. Yeah, so I have written up to this term, and I have not written the higher terms. So now what we'll see here, so like why I have not written the higher terms, because you will find that they will like you they will automatically go to zero. uh, so 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 let's see that how. So I think it will go to zero from here itself. So we need only up to uh, these two terms. So how is it, like let's write it down. So from the uh, so first term we have just usual ladder operator A, then plus the second term. The second term, what we'll get, you take the commutator. uh, so term by term. So what you will get from the second term, you will get alpha star a commutator, which will basically be 0 minus uh, alpha a dagger a. So this is what you will have from the second term. So yeah, so from the second term you have this. And now like from the third term, the this term. So what you will have. So uh, okay, let's solve the second term, and then we can put it uh, in the third term, because the result of the second term immediately follows to the third term. So so if I solve the uh, second term here, so this one will go to 0 and you have minus alpha, and commutator of a dagger a is minus 1. So so this is commutator of minus identity operator. So that means minus minus is positive, then you have plus alpha. Okay, and then you see you got plus alpha. So commutator of this and this is giving you some number. It is a complex number alpha. So again, the commutator. So like so following from here, you can write this to be uh, alpha. So then commutator of this and this will give you 0, because commutator of this operator and the number. So commutator of operator with a number, or the number by itself means something multiplied with identity. So commutator of some operator with identity operator is 0. So that is why finally you will have a plus alpha. So I think this is clear, or is this clear? Okay. So anybody else, if not, they didn't understand, like, please you can let me know. uh, so at the end, like the same way, you can prove this one. So this is just again following the same rule here. So yeah, you can get it, like you can if you go to your portal, if you log in into your portal, so there will be some section on problem solving sessions. So you have to go to that problem solving sections, and then there you will find the other details, like the recorded lecture videos and the notes. And so there will you I think you will be taken to a spreadsheet, a Google spreadsheet, so where you will have the specified links. So from there you can find the uploaded PDF files of this discussion, of this presentation that we are having right here, and along with the recorded YouTube video. So uh, yeah, thanks. So finally, the last point here. Um, uh, if you sandwich this Heidegger operator between these displacement operators, then you again find that this Heidegger operator will be displaced. So will be displaced by minus alpha identity operator. So that also you can quickly. I mean, like, you have to follow with what we just did. I mean, immediately before this problem. So the same thing you have to do here. So this is alpha star a minus alpha a dagger. Then you have a dagger exponential of alpha a dagger minus alpha star a. So yeah, this will give you again. You use the BCS rule. BCS rule. You will find a dagger plus alpha star a minus alpha a dagger with a dagger. Then you will have something 1 by 2 factorial uh, with alpha star a minus alpha a dagger with this whole thing here. Uh, so again, you will find that this term will go to 0. So from this second term, you will get minus alpha. So this is basically equal to minus alpha. If you solve it, you will find that not. I think this is not minus alpha. So this is a plus alpha star. So it's minus 6. This is plus alpha star. So you will find this to be alpha star. Okay. So yeah, you have to repeat the same thing which we just did before. So if not clear, like I can show you. Like uh, so, if anyone has any confusion with anywhere previously what we have discussed, like please let me know. Like whatever not clear, like you can speak. Okay, so I hope like if you have understood all these points about uh, displacement operators, then we'll see how we can use these displacement operators to understand coherent states in this following problem. So, so again, as I was telling you before repeatedly, that coherent states can be created using these displacement operators. So, uh, so first let's build this coherent state alpha from the ground state 0 using this displacement operator. So yeah, so first what we have, so now you'll see that like um, it would be more useful to use the other definition of displacement operator which I like uh, given at the beginning. I mean, at the beginning we found the displacement operator is defined to be exponential of alpha uh, alpha a dagger minus alpha star a, and also we also defined it using the exponential property, the decomposition of exponential factors. We found that it can be further rewritten as minus of half magnitude alpha square, uh, then exponential of alpha a dagger with exponential of alpha a. So we'll find this expression to be more useful now. We'll see how, because if alpha is what we get upon operating d alpha on 0, then let's see if I write exponential of alpha a dagger minus alpha star a on 0. So what we will have if I do this operation, so from the first I have to first basically expand this. So uh, so if I expand this, so I will have identity operator. So I am basically doing the exponential expansion. So then alpha a dagger minus alpha star a plus, so this is basically doing the expansion of exponential of x operator, where I have identity operator plus x operator plus uh, x square operator uh, over 2 factorial and so on. So that is what you have to do here. So again, I can write alpha a dagger minus alpha star a square over 2 factorial, and so on. You will have other higher uh, expansion terms, and all of them acting on 0. So now you will see that like we can operate this one with 0 easily, but then we have to do a lot of work to operate this on 0. because first we have to evaluate the square of this uh, thing inside the parenthesis, and then that will give you like four terms, and then again individually you have to operate on this zero, and then again there exist higher terms which I have not written here. So again they will individually, like you have to find out the pattern, like there will be a cubic term which I have not written here. So again you have to first evaluate that cube and then you have to operate. So you will find that this is a bit of a uh, hard work. There's then the one, if you use the approach using this expression of d alpha. So if you do that, like what you will have, so let's uh, write again alpha. uh, if you act exponential of minus half alpha square, exponential of alpha a dagger, exponential of alpha a on 0. So now you can do the same business of expanding the exponential. So let's expand this exponential. So you will have identity operator plus alpha a plus alpha a square over 2 factorial, and again you will have more such expansion terms like cubic and fourth power and so on. But what you will see here, at the last exponential which we have just expanded, so this had the argument of alpha a. So upon expansion, we found identity operator plus ladder operator a, and then ladder operator a square. So so this lowering ladder operator when acts on 0 gives us an advantage that a when acting on 0 is straight away 0. So it will make like our computation very easy, because all this term when they act on uh, uh, 0 is eventually 0. So so I will have only the identity operator acting on 0 will basically give you 0. So so this will turn out to be simply exponential of half magnitudes alpha square, then exponential of alpha a dagger, then identity operator acting on 0 will give me 0, then all other will automatically go to 0. So all of them are 0, so all 0. So uh, so finally I just have this thing. So again what I can do, again I can expand the this term. So I have identity operator plus alpha a dagger plus alpha a dagger whole square over 2 factorial and so on acting on 0. So now what you have is exponential of minus half alpha square. So the first identity operator when acts on 0, it is simply 0. Then alpha a dagger when acts on 0. So remember what happens when a dagger acts on any number state. So it gives you n plus 1 times n plus 1 state. So if it acts on 0, then it will give you a square root 1 and 1 state. So that means it will give you uh, alpha square root 1 1. Then from the second from the next term, you will have to operate alpha two times. You have to operate a dagger on the 0 two times. So so this is like alpha square a dagger on 0. So if you see, this will give you alpha square uh, a dagger square root 1 and 1, and then this will eventually give you alpha square root 2 2. So you will find here alpha square, and also you have a 2 factorial below. So let me write, so square root 2 over 2 factorial and 2, And same way, like so so okay, so you will have other terms also which are not zero here. So what you see here, like you can find out half of alpha square 0 plus I can write this as alpha 1, and the second I can write this as square root 2 square root 2. So this will be like alpha square root 2 and 2. And then from the next term, like which I have not uh, evaluating here explicitly, but you can check here, this will be basically alpha cube over uh, something, it would be something 6 and 3, and so on. You will find more terms. So what it is at the end it is becoming is basically alpha square 0 plus plus alpha square over square root 2 factorial 2 alpha cube over square root 3 factorial 3, and like this it will go. So you are getting a nice pattern over here, that this is equal to exponential of minus half alpha square. uh, uh, I can write this as summation of, I can generalize to n going to 0 to infinite. So you can see you are getting infinite number of n states. So that is what the whole point which we were starting, that coherent states are made of indefinite number of quantas which are n states. So alpha to the power n square root n factorial n. So, and this is what your precisely is your coherent state, which is made of indefinite number of quantas. So, yeah. Now you can also check, if you operate a on this alpha, you will get alpha alpha. You have to do some little bit of task to, so it, I mean, it won't appear straight away. So, but you can prove this, that this should be a eigenstate of this operator a. So. Yeah, so this is how you can construct alpha from the displacement operator, but if you use this definition it will be more easier to get. So is it clear, or any problem here, or anything not you able to understood, or
Sir, we are constructing
uh,
the
s-
displacement operator with the like zero state, right?
sorry, yes, could you just speak little louder?
We are constructing the alpha with the
Yeah, yeah,
displacement operator.
right.
That like that alpha is a coherent state.
Yeah, it's a coherent state. Yeah.
Can you scroll it down?
Yeah, sure.
No, scroll it down.
Okay. This,
Yeah, yes.
yeah.
So the summation tells me about the linear combination of the state.
The summation tells you what?
That tells about the linear combination of
Yeah. The summation is telling you that it is composed of linear superposition of many number states. So indefinite number of number states. So indefinite number of photons you have. So
sir,
so
but
like for
how you
example,
came in the first
for sorry. Uh,
sir, how you came in the first place that displacement operator on like zero state gives some coherent state?
Yeah, so that is what the property of displacement operator. So it takes you like from one of this number state which we started here, zero, to a to some other state, and that other state eventually has a linear combination state. I mean this alpha. So like
So
it's
we are
just
like checking that what would be the answer if the displacement operator operates on.
no, no. So what we did, like first we tried to operate this displacement operator, let's say on some state like the ground state. So and after operating this displacement operator, we got some outcome. This, let's say this is the I mean the final outcome you got after operating the displacement operator. Now if you operate a on this state, you will get alpha alpha, and that further will confirm you like that this is your coherent state. And itself, and also you can itself see that this alpha is made of many number of quantas. So it's not like for example n like I mean if you have some n state, so it only tells that the oscillator is made of only, like let's say only if n equals to some 8000, so it only made of 8000 photons. But if you have alpha, it tells you that it is made of it can be 8000 photons. It is a linear superposition of 8000 photons, like 7000 photons, or any n value, and so on, like at the same time you have it. So this is purely of a like a quantum oscillator, like which you see there. But here when you have this linear superposition, it this will have, this will attain some kind of classical nature. So we'll see again here in a moment. uh, so yeah, like am I able to like clarify your point, or
Yeah, yeah, yes.
okay, yeah. What is the first term of alpha exponential alpha inverse? Yeah, you can think of it like it's like uh, if you're talking about this particular thing. So yeah, this is basically a normalization, overall normalization factor. So maybe I mean yeah, like we can check how this is a normalization factor. Just maybe the next question is actually is on that itself. So yeah, so we'll see. So like I think if we try to answer this point, then that will clarify your what's the point of having exponential of minus alpha square over 2. Yeah, yeah, thanks. So yeah, so if moving on to that, so if there is anything else, like please please ask. Meanwhile we can uh, see the next following question. So the next following question is actually on the inner product. So it follows quite exactly. Yeah. Let's see. Like we have to find the inner product. Basically, you have to compute what is common inner product of inner product of two coherent states. So let's so we have introduced a new coherent state. I mean we have introduced a new coherent state with a new label. So let's write that as coherent. Let's write that coherent state is beta uh, state, uh, exponential of minus half beta square summation. We will introduce a new running index, this dummy index uh, for the beta state. M going to 0 to infinite, beta to the power n m over m factorial m, and previously we had alpha. If you take conjugate of alpha, you will have this alpha. So this will basically give you exponential of minus half alpha square, n going to 0 to infinite, uh, alpha star. This will become alpha star. So if you have alpha here, if you take conjugate, then this will become alpha star n, then n factorial, and this will be bra n, right? And now you can take the inner product. So you have, I can pull this and this factor outside. So because these are some numbers, so I have half, negative half of magnitude alpha square plus magnitude beta square. Then I have two running indices, one m going to 0 to infinite, and also n going to 0 to infinite. Then I have alpha star to the power n and beta to the power m. Then uh, within square root I have n factorial and m factorial, and this n, and the inner product of n and m. So remember, these are number states. So these are orthonormal states, because yeah. So if you remember, these number states are orthonormal states. So what we can write here is following. So I can write exponential of minus alpha magnitude alpha square magnitude beta square. Then again summation running from m0 to infinite, and summation running n0 to infinite, alpha star to the power n, beta to the power n factorial m factorial, and this I can write as Kronecker delta nm. So right, and okay, and this Kronecker delta, what it will do? So this will enforce. So this Kronecker delta, it means it will be only equal to one if n and so I hope every one of you are familiar with this. So this is one if n is equals to one, n is equal to m, or zero if n is not equal to, sorry, n is not equal to m. So this is what Kronecker delta is. So that is why I will have exponential of minus half uh, uh, alpha square beta square. Then I will have only one index right now, because n is equals to m. So I will let me write it by n going to 0 to infinite. And so instead of alpha star to the power n and beta to the power m, I will have alpha star beta whole to the power n, and uh, square root n factorial, and square root n factorial is basically n factorial. So now we have simplified quite a whole lot here. So now we just have exponential alpha square beta square, and this one I can write it as exponential of alpha star beta. So this is nothing but this is entirely a exponential expansion of this exponential of alpha star beta. So now if you see clearly, what we found here, alpha, inner product of alpha and beta uh, gave us exponential of alpha, alpha square plus beta square, and I can, yeah, exponential of alpha star beta. If I do the other way around, beta alpha inner product, then I will get exponential of, you can check this, I will get this beta star alpha. So that means if I take alpha beta magnitude square, that means uh, alpha and beta alpha. So this will give me exponential of, you can write it down, alpha square plus beta square minus alpha star beta minus beta star alpha. So remember, all this inside this exponential are just numbers, so I can just treat it as normal exponential factors. Like there is nothing non-trivial here, like as we were dealing with operators. So now there is no operator, so you can just pull it inside one exponential. So now what you see here, you will get this exponential of minus magnitude of alpha minus beta square. So now this will answer what you were trying to ask, like why there is a factor of alpha square and beta square, this exponential. So if I take, let's say, uh, yeah, so what we have right now, so alpha beta square equals to exponential of, right, so this is what you have. So if, let's say, alpha and beta are same, that means alpha and alpha, if I take magnitude square, it is giving me uh, identity operator, sorry, this is giving me 1. So if this is giving me 1, that it tells that alpha and alpha is 1. This implies alpha is a normalized state. So if we wouldn't have this alpha or beta in at the beginning of our definition, then we would not have got 1. So we are getting 1 because of this alpha, which was there as a prefactor uh, with the exponential of minus alpha square by 2, and that itself is leading us to the fact that alpha is in normalized state, because the inner product just yielded to be just gave us 1. So this one signifies, or this one basically implies that that alpha, that with the definition which we started, is a normalized state. So that clearly implies that this presence of exponential of alpha square factor is playing the normalization constant role of the normalization constant. So I think that will answer your question, and also, yeah. Yeah, and also if anywhere, like somewhere down here, if maybe any given step you didn't follow, like please just let me know, like we can discuss, we can clarify here anything, or any other question. You can ask like any other question which is also not related here, like we can talk about some related topic of, I mean, some question of the previous related topic as well, like because all of them like are essential to uh, I mean essential to carry with you, like I mean uh, somewhere down you need the ideas of the previous properties that you have studied. So it's better, I mean there's nothing strange to feel about like asking some previous question as well. So just let just trying to let you know, you are free to ask. So yeah, so anything if not clear, please, you can speak here, or you can also drop the message here. uh, there was one more question over here. So calculate the mean number of quanta in this coherent state. Uh, okay, so mean number of quanta. So I think this is number 3. So mean number of quanta means we have to take the average of number operator in the coherent state. So what it will give? So number operator means a dagger a. So if I do that, yeah. So what I can do here? So I know when uh, a operates on alpha gives alpha alpha. So this implies if I take the conjugate, it will give me alpha a dagger equals to alpha alpha star. So you can see here I can split this into two parts and use this and this uh, like expression. So I will have um, yeah, I have alpha a dagger and I have a and alpha. So this will give me uh, alpha alpha star and alpha alpha, right? And this is what you will get is alpha square, because alpha and alpha, as we found out, that they are normalized, and alpha square. So now what you are getting is basically, so this alpha square has also another meaning, that this denotes the average number of uh, photons you will like can be found within the coherent state. So yeah. Okay, so this is just a bit straightforward. Like so, is any question you can ask? Uh, so like you. So this is clear, or if anything not you are able to understand, please you can speak. So last we have one more question, and this is like is interesting to know, and it's also important. Okay, so yeah, average number of photons. Yeah. Um, so average number of photons. You mean you need to. So like, what you didn't get? Like, I mean, this statement you didn't get, or what? Uh, So in the question, we were asked to calculate the mean number of quanta. So quanta means we have to calculate. We are talking about number operator. So it's like calculate the mean of position or momentum. So just like we have to compute mean of this number operator here in this question. So and we know this number operator is a dagger a. So if I yeah, if this number operator is a array, I have to use this a array, or basically I have to sandwich this a array between this alpha states, between the coherent states, because we are like, if you remember, like last time also, as we were trying to do for any expectation value of any physical observable, we need a state under which we are trying to know the average outcome. So here we are trying to know in the coherent state. So we will know the average outcome of the number of quantas in the coherent state. So you have to sandwich this alpha, or basically you have to sandwich this number operator between this alpha coherent, or the coherent states. And from the coherent state definition, as we have started our discussion from this itself, as we know that these coherent states are eigenstates of the lowering operator, so we can use this feature here. So when a acts on alpha, so it gives alpha and alpha, and if I take the complex conjugate of this, it will give me this. So uh, so uh, so then I can use both the facts here. I can use a acting on alpha, and then bra of a dagger. So I can just separate it out into two parts, and write the right hand side of this expression. Basically, I'm using uh, uh, this over here and using this over here. So then I have this. So this is basically magnitude alpha square and alpha. So this and alpha inner product. Just moments ago we saw that this is a normalized state. So this inner product of alpha and alpha is 1. So this is right here. So that is why you only have so for this particular is it is the number only using number operator. Yeah, so we want to know the number of quantas or number of photons. That means you have to use the your operator n, so which is given by a diagram. So yeah, so that gives you the average. So alpha, magnitude alpha square is basically the number that tells you that this is the average number of photons that is contained within the coherent state. I think this is clear to you. Yeah, okay, thanks. So last we had this. This is a interesting to note here, and then with this we can end right here. Uh, so what we have at the end is we will take the same expectation value. So if you see the question over here again, calculate the expectation of x square, p, and p square in the state alpha, and consequently show the minimum uncertainty. And why we are bothered about minimum uncertainty here, we will know, like, so yeah. So first, if you take the expectation of x in the coherent state, so again remember, like, we have taken expectation of position operator previously in the last discussion in some arbitrary linear combination state, but here we are taking the linear combination of state that gives rise to coherent state. So we are taking the expectation in the coherent state, and x operator, if you remember, even last time we have used this expression 2m omega a plus a dagger alpha. So again, which is also, I think, let me check, is this yeah, this is given, and for p you have this. So we'll use them to compute our expectation. So yeah, so then I can take this factor outside, and I have alpha a plus a dagger alpha. So I will have h bar 2m omega alpha a alpha plus alpha a dagger alpha. So and you will find that I will have h bar 2m omega. You will get alpha over here, because when a acts on alpha, it gives you So this gives you alpha alpha, and from here you get alpha alpha star. So that is why you will have alpha plus alpha star. So this is the expectation value you will get. Now if you do immediately, like what you will get, let's say expectation of x square. So again, alpha, you take the square of this thing. You have to take the square of this thing. So h over 2m omega. So you will have a square plus a dagger plus a dagger a plus a dagger square, and this whole thing is sandwiched between alpha. So here you will have many four such terms: alpha a square, alpha plus alpha a dagger, alpha plus alpha a dagger a, alpha, and last you have alpha a dagger square alpha. So um, yeah, so if you see, so from here you will get alpha square, and from here you will get minus alpha star square, and uh, if you see, like likewise you will find out, uh, like let's see these two terms what you will find. So alpha, when it's on a dagger and alpha, so you will get from alpha alpha from the right part, and from the left part you will get uh, alpha and alpha star. So this is like alpha star alpha you will get. But from the second term you have a dagger alpha. So this one what you can write, so remember, since a dagger is identity operator, but you can write it as a dagger minus a dagger a equals to identity operator. So you can write a dagger as identity plus a dagger a. So you can use that here. So that will give you alpha identity plus a dagger a alpha. So that means you will have uh, 1 plus alpha alpha star. Yeah, that is what you will get here. So finally, if I write it down, so x square. So we have individually found out what would be the outcomes of the inner products. So this is basically h bar over 2m omega. If I So I'm directly writing down the answer. So I mean, we have found out the all the inner products. So it's just simply, if you just simplify, you will find this to be alpha uh, plus alpha star whole square. I think this is the whole square. Okay, yeah, this is whole square, right? So this is what you will have. Uh, um, and the same thing like we did for position and position square expectation, so we'll do for momentum as well. So for momentum, same thing you have to do in alpha. So momentum operator, again you can check, it is given uh, uh, in the question, like you have to use this form, this one, I over square root h bar m omega by 2 h bar, sorry, m omega by 2 uh, a dagger minus a alpha. So this will give you h bar m omega by 2 alpha a dagger minus a alpha. So so you will have h bar m omega by 2. So again this is simple, which you have alpha minus alpha star. uh, okay, so there will be this will be alpha star minus alpha. Okay, so again, like I'm not doing the momentum square average, so the same type of computation you will also see. So you will have h bar m omega by 2, and again you have 1 minus uh, alpha minus alpha star square. So using this, all what you can do, you can find out the uncertainty or the standard deviations. So first let's find out the standard deviation position. So that is what you know is defined as x square expectation minus expectation of x square. So this will give you, if you do that, uh, so so x square expectation is this, and expectation of x is this, and again you have to take it square. So like if you do that, you will find this to be h bar over m 2m omega. And same way, if you calculate the expectation in momentum square, in momentum, so you will have p square minus p. So this you will find out to be h bar m omega by 2. Now if you uh, do this sigma x times sigma p, uh, this is basically the uncertainty. So I'm trying to calculate what is uncertainty, delta x and delta p. So uh, so if I do this, like I found here following h bar m omega by 2, and this is giving me h bar by 2. And now you remember, like from uncertainty principle, it is always said that uh, uh, the uncertainty principle always tells us that it should be always greater than or equal to, this is always greater than equal to h bar by 2. But here when we took the uncertainty, or when we evaluated the uncertainty sigma x and sigma p in the coherent state. So remember, all this expectation we are calculating, we are calculating here is using this coherent states. And using this coherent states, when we calculated the expectation values of position and momentum, and then when we are using it to compute the uncertainty, we are finding it to be exactly h bar over 2. So that is like the minimum uncertainty. So it has the minimum uncertainty. That means it is clearly telling us that delta x and delta px is exactly equal to h bar by 2. So that means there is very less uncertainty uh, in knowing the position and momentum simultaneously. So uh, it tells that this is very closer to the classical outcome of the outcome of the position and momentum we will have when we are dealing with this type of quantum system, which are described by coherent states. So this tells that alpha uh, corresponds to the minimum uncertainty state. So so they are more close to uh, classical outcomes. So basically, classically behaving states these are. So that is why we were trying to make this point, like how so like So even if you try to see if, in this coherent state, if you try to evaluate this x in this alpha, so this will give you x naught something cos of some phase you will find, and this is what you also get when you try to write the expression for the classical oscillator. So something same you will find if you take the expectation of x in alpha. So you manifest classical results, classical outcome out of these coherent states. So that was the point we should try to remember here. Yeah. So anything not clear, like, or uh, yeah, this is something finally what we can draw from this all the problems that we discussed today. So yeah. So anything not you followed anywhere at any point throughout this discussion? Uh,
Sir, I have some doubt not
yeah.
related to this.
Yeah. Yeah.
Sir, the density operator, I have doubt about density operator. Uh, the,
Density of
is it density operator?
density operator. Okay.
Yeah, is it like it projects some state vector and spits out the probability of that state, or can be something like that? And I also have doubt what can be how the projection of sorry density operator can be used on a mixed state.
How the density operator can be used?
Uh, uh, what is the outcome if the density operator operates on a mixed state?
Okay, on a mixed state. So, like, I mean, so density operator is basically a different, like, is another way to, like, for example, when you had when you had pure quantum system, like, which means the quantum system are isolated, like all the quantum system, even here the quantum harmonic oscillator which we have, I mean, uh, yeah, the quantum harmonic oscillator which we have studied, or infinite well, so these are all we have studied, like, considering that they are very isolated, like, system, which means this system do not interact with any outside world, so they are completely isolated system. So this type of system we can explain, or we can denote using some state representation, like we can denote some definite state for the particle which is inside harmonic, which is characterized by harmonic oscillator or infinite well, then we can define a state. But if we have that system interacting with outside world, or maybe there are ensemble of harmonic oscillators, not just one, there are many such, then in that case we cannot just simply represent by a state. So then we have to go to density matrices. So and there we use this I mean, this outer product of this states, where we get here the each entries basically gives the ensemble like probabilities. So this is something you also do very often in statistical uh, physics as well. So this is the difference, like, because you are not you are dealing with some not, I mean, so this can be not just pure state, this can be many, I mean, what, this can be mixed states. So basically here you will have uh, uh, so this kind of linear combination, so there will be c1 c2. So all this tells that there are many such number of like what ensemble of harmonic oscillators. So so if you have only isolated harmonic oscillator system or infinite well, like, you can uh, do the entire quantum mechanics using using this only state representation. You will use only single state to define the quantum nature, the quantum state of the particle. But if you have many such, or if you have the quantum system interacting with the outside world. So if it is interacting with the outside world, then you will find that it will be psi interacting with some other state. This is phi is known as environment. So this is, I'm giving you a very qualitative. Like on a surface level, uh, implication, if you would say. But like to understand mathematically, like we have to go through from the beginning. Like we will, if possible, maybe in the next class, or we will discuss that and also do some problem. But
Sir,
roughly you can understand this way.
sir, that is okay, sir. But is it always presents a probability of a vector, state vector?
Probability of
A state vector, because this operator can operate on a state vector and give some constant, right? Some
yeah,
common
yeah,
constant.
yeah, yeah, yeah,
So, so if it square it, then it's mean a probability, right? So
yeah.
it
It's
means
if you take the square, right. Like you, if you take the square, you are telling you will end up with getting probability, right?
yeah,
Magnitude.
that's what
Yeah,
I'm saying.
yeah. That will give you that, right. Then what else you like this? I mean, this is just simply the outer product, so this is not itself is a probability. If you take the square, then it can give you the the magnitude square. uh,
Okay, sir.
yeah, the magnitude square will give you the probability. Anything else? Uh, yeah, you can yeah. Like please give examples of some higher value uncertainty with respect to uh, like I don't understand exactly some higher value uncertainty. Like if you like for example, if you take some for example, if I give you some arbitrary state, let's say some psi, um, like any arbitrary state psi 1, if I give you, you take it to be something c1, like phi 1, sorry, not phi 1, let me write this as 0 c2 or c0 2, or something like c6 6, and there is some more state. Let's say this is again made of two states, like 1 by root 2, like 0 and 1. And you take many such number of linear combination, any arbitrary linear combinations, even uh, even infinite number of uh, combination as well. But in none of them you will find that a minimum uncertainty would be uh, uh, equal to h bar over 2, that which we have seen here. It would be uh, always greater than h bar by 2. So if you have precisely the state which we have defined at the beginning, or not even in this problem which we have said it, if this is the state, then or not this, this is, yeah, if this is the state, then this is precisely the coherent state for the harmonic oscillator which we have generated by operating the displacement operator on its ground state. So then you have constructed a coherent state for this harmonic oscillator, which means you have defined your quantum harmonic oscillator in a state which has more closer classical resemblance. The outcomes will have more closer classical resemblance. So then, if you take the uncertainty in this alpha states, then you will end up with h bar by 2. But if you have some other states for this quantum harmonic oscillator, like any other arbitrary. even if it is more number of other terms are also included, then you won't get exactly this. So it will be always greater than h bar by 2. So I think that is what you are trying to do. Uh, okay, yeah, yeah, that's good. So uh, anything, uh, yeah, anything not clear, or if you had any other issue, please let me know. Uh, yeah, so like we are more or less done for like we are yeah, we are done for today. So we can again come back for another live session again next week. So if anything, like you can go through the entire discussion which we had. If anywhere at any point which you missed it, or you found difficult, or anything silly even which you uh, didn't understand, so please you can let me know next time, or you can also let me know immediately if there is some immediate question now, or we can stop here. We can meet again uh, around this time next week. So okay, I see if there is I see there's no other question. Uh, okay, okay. Also, we are like over the time. Like so, time is up for today. Let's meet again um, next week around this time. Like, yeah. See you until. Yeah. Thanks.